Okay, so today I'm presenting on the analysis of the ruthenium chloride density state when G over T is much less than 1, so when it's paramagnetic. And so ruthenium 3 chloride exhibits interesting catalytic, photochemical, and magnetic properties. As you can see, it is a 4D transitional metal with one unpaired electron on the ruthenium 3 plus. It's arranged in this nice honeycomb lattice, and the interlayers are stacked with the weak van der Waals forces, which allows them to be cleaved into thinner layers. It can be modeled as a Kiriev quantum spin liquid, which allows it to be exactly solvable. However, as the size of the system increases, the number of spins increases, and the problem no longer becomes solvable due to the computational time that's necessary. And so fortunately, it can be solved because it follows a probability distribution, as you can see here, which was calculated using the equation for combination. So it starts off very close to 0. When you hit 16 up, you hit approximately 15-ish, little over 14% of probability, so that's the highest charge. And since it follows this nice probability distribution, the Monte Carlo sampling method can be employed, which allows us to then calculate it from a much smaller sample and then be able to calculate these different energies and magnetization values. And so the method that we used was we input the parameters for each, we set up the boundaries, and then we generated random microstates and calculated the resulting magnetization, which can be calculated because of the sum of all the spins of a given microstate, and then the energy from the Ising Hamiltonian. And so what we found was that as you increased magnetization value, which we classified as B, it resulted in the energy becoming distribution becoming wider, and this will correlate later on with Payman's findings, where when the which you can see here, when the spin-spin coupling constant is equivalent to your magnetic field, your energy range for your microstate, they're all very, very close to 0. Whereas as you increase your energy microstates, they distribute out and you start getting negative values as a possibility. We also did that where we decreased the magnetic field in relation to B, and again you see the same thing, is that the larger the magnetic field, the further they are from 0. And then we evaluated the impact of the unpaired number of spins on the energy of the microsystem. We first tried it with J equals B. However, that did not yield good results. So then we made our external magnetic field 10 times that of our spin-spin coupling constant. And then we did get the expected results, where when all of the spins are aligned with the magnetic field, you get your lowest ground state, which would be expected because everything's aligned. When we align all of the magnetic spins against the magnetic field, we actually get a value that is not exhibited within the density of the state graph generated using the Monte Carlo method. And this is because the Monte Carlo method doesn't exhibit all of the peaks. They only take 20,000 random ones that it picks. So those that have very low probability of being picked because they don't have very many ones where they're the same, they end up not being illustrated in this graph. So this is actually up here. And then likewise, when we have the microstate with 8 down spins, you can see that that is approximately halfway between that of all of them being downspin and half of them being downspin. So as we increase the number of unpaired electrons, because that's what this M1 represents, is how many is unpaired, we increase the energy. So likewise, when we have them half and half, so we have no unpaired, we end up right in the middle. And then once we have 8 extra unpaired electrons that are going against the magnetic field, as expected, that is about halfway up. And then, as I said, this one is no longer presented on the graph. And so in conclusion, we confirmed the expectation that the magnetic field increases as a resultant energy range of the microstates due to Zeeman splitting, and then that the energy of the microstates is dependent on the number of unpaired spins aligned against or with the magnetic field. And with that, I say thank you and ask if there are any questions.
You can see people applauding to everyone in the audience. Yeah, thank you, Crystal. Any questions any questions in the audience? Yes, John.
If you could go back if you hello. If you could go back if you find actually forward one more, sorry. Or second to last slide, sorry. Yes. I guess my question is, what height are you expecting for the highest peak that's cut off? Like, I guess, like approximately, where do you think it would be on the y-axis?
On the y-axis, it should be, because it'd be the same probability as the A. It should be pretty close to this 0 mark, just like A is.
Okay, sure. Thank you.
Yeah, thank you. Any more questions in the class? Any questions from online?
I do actually. Why is the kit of quantum spin liquid important in this research?
Oh, for KDF quantum spins allow you to actually be exactly solvable. Whereas, so quantum spin liquids are interesting because, and that's why we're interested in these ones, is they're materials that will allow for potentially levitation, will allow for a variety of uses so that you won't lose heat. But when you get to the KDF quantum spin liquids have the extra advantage is that they're exactly solvable on a tri-coordinated lattice. And so the only issue we have with like the sampling of our number of spins going up to 32, and that's where it's still exactly solvable. It's just the computational time to solve it would go on for too long. So that's why we use this probability distribution and use the Monte Carlo method to approximate the actual solution. Does that answer your question, or is it a different question?
That is great. Thank you.
I have a question for myself. So, Crystal, you have a peak A and the panel A when all spins are downwards. Other situations when the microstate with all spins downwards, you will not the minimal energy state, but something different. Can you please comment on that?
Yeah, well, like the one that I sent you when I was confused, Dimitri, was for the one where when we had the J equal to B, and that's where I was confused, and then we ended up making the magnetization 10 times greater, because then the spin-spin coupling overcame the ability of the external magnetic field, and my J value for my when everything was spin down was about here, when my J equals B, and my other values were actually not, so it wasn't the spin ground state.
Okay, and what if you just put the direction of magnetic field? If you use minus B equals like minus 0.1 instead of.
Yeah, that would also affect it, because then it wouldn't be all aligned with the field anymore.
Okay, yeah, good. Any more questions from online? Oh, Steven, yes, please.
Working off of Dr. Killing's question about and your response, the situation when J was equal to E, did you notice a result that looked more like your panel C there, where you have an equal number of pairs, or all paired spins, or was it more similar to B or D? If you don't have an answer.
For when I did the J equals to B, I didn't do these type ones when I did J equals to B, because I was just starting at this point when I found out that it wasn't matching right.
Okay.
Okay, so please join me in thanking Crystal once again.